Welcome to circuitvalue.com. I'm Gaurav. Today in this video we're going to talk about this HMC8042 power supply from Rohde und Schwarz. Somehow I managed to acquire this unit, but it is faulty and it doesn't turn on. We will try to plug in power soon and we will try to compare it with my HMC8043. I have two HMC8043 and this one broken HMC8042. These are really nice 100 watt power supply. This one particularly be able to deliver 5 ampere on both of the channels, and total power it can deliver is 100 watts. That you have to balance. Software can also help you balancing that. Let me show you my HMC4032. So this is my trusted HMC8043. It is a 3-channel power supply. All 3 channels can deliver 0 to 32 volts and 0 to 3 ampere. Total power of this power supply is only 100 watts, and this 100 watts is distributed between all 3 channels. One channel can deliver maximum 33 watts, but you can parallel and series these channels to get whatever the power you want. Now getting back to our repair candidate, this HMC8042, it's a 2-channel power supply, 0 to 32 volts and 0 to 5 ampere on both of the channels. On one channel this is maximum 50 watts. So let's take a look. We will try to plug it in and we will see how does it goes from there. So right now you can see this unit is plugged on, and I have turned on the supply as well, and on the front of the unit I do not see any power. If I press the button, nothing happens. I'll show you. The unit have received the power. Unit has a SMPS sitting on the top and it must have power. So you can see inside the SMPS, which is sitting on the top of the primary board. It is getting power, but the unit itself is not getting power. This is the fault. First of all, we need to find out what is wrong with this unit and why it's not getting power on. Maybe there is a fuse blown, or maybe there is something else is wrong and we don't know yet. So we will take it apart and we will see what does it takes to repair this system. So let's first take screws out. I believe this is the thing, it's too small. I believe this screwdriver will do, yeah. So screws are off and this back pads are off. There may be a screw in the bottom. There is no screw in the bottom. This should just slide off. So this is our instrument. This is how it looks. At least on the top side it looks pretty neat and clean, and doesn't appear to be anything wrong with it. But first of all we need to take out this board. Maybe I'll show you one more time getting powered. Then it does get powered. So you see that LED? It lights up. This is the LED which you see in my HMC8043 as well. And this instrument is pretty much same. And I have repaired my HMC8043 as well. So I believe I can repair this HMC8042 as well. So let's turn it off and let these capacitors to discharge, and then we will try to dismantle it further. These 2 screws need to be taken off. They need smaller. Toothpick. So now I have T10. I do not want the screw to fall into the instrument. I'm holding it with my hand. So both of the screws are out, and you can see there are locks on this side, and this thing we can unplug the power cable, unplug the ground as well, unplug this cable as well, unplug the fan as well. So this power supply unit is completely plugged off, and we need to slide it in the front, something like this, and plug it out. So we have the power supply unit out, and now we can investigate further what is wrong with this board. Is not faulty. We can measure the output as well here. I remember from my last repair of HMC8043, there must be around 50 volts, and there may be one secondary supply of 12 volts or something like that must be present there. So we'll find out what is wrong, and we will try to repair on the primary board. So this is how primary board looks. This is the channel number 2nd, and this is channel number 1st. There is a empty footprints for first channel as well. If this would be HMC8043, then you will see these components as well populated. As you can see, this thing is controlled by a PIC microcontroller, and there's a place for this, for one channel, second channel, and third channel. And there is some isolation transformer. So when you get 50 volts from here, and these two transformer delivers isolated 2 channels, because these 2 channels are isolated. So they do deliver isolated DC-DC conversion, 50 watts each of the channel. And this is, or this, I don't know which one it is, but one of them is going to be switching element for this particular transistor transformer. I believe this is the diode, and this is the switching element. Yeah, this is the diode, and this is the switching element. I remember it from my HMC8043 repair. And this is the linear regulation area, and this is the linear regulation for front end, for the final current delivery to the front end. So, and on the back, this is the thing this is the PIC microcontroller again, along with the Ethernet PHY. It handles the USB and Ethernet. I'm not sure if it handles the USB, but it definitely handles the Ethernet. And USB may be coming from this board. You can see there's a big fat microcontroller in front of us. Maybe not microcontroller, maybe it's just a CPU, because it has RAM and flash outside of the chip, and there are some maybe shift register or something like that to drive LEDs or pins or something like that. There's a RTC battery, because this instrument can log as well, and this most likely is a connector for the LCD, which is going in the front, and this LCD. So if I inspect it, I do not necessarily see anything wrong with the instrument. Let's look at the back. Sorry for the flash, I do not have very appropriate lighting setup here, because it's on my secondary bench. So this is the area unpopulated for the first channel, and this is for second channel, this is for third channel, and we need to look pretty much deep and find out what is wrong with it. And I see there are at least two fuses visible to my eyes. There must be at least 3. If this belongs to this channel and this belongs to this channel, then yeah, then we have 2. And where is the third fuse? I have no idea. Yeah, so there are at least few fuses there. So we'll first measure with fuses, and then we will go ahead. What does it say? Yeah, there's a one fuse here as well. This is the fuse which powers everything. So if this is blown, then you will not get the front panel soft power button. This need to plug. This thing I know from my HMC8043 repair. So we'll first measure this fuse. Okay, we already got one thing, and this fuse is blown. This fuse is blown too. So we'll try to replace these two fuses, and then we will try to investigate further. There is a PTC element here. It's definitely working. So this fuse, this fuse appears to be working, and these two fuses are definitely blown, and we will try to find out if there is something else wrong with the instrument. At least on the front I do not see anything wrong with it. Let's take it further apart. Maybe we will take out the complete PCB out so that we can inspect it properly, because if fuses are blown, they are blown for a reason. They are not just blown for a fun. So to take the front panel off, we took out 4 screws, and we're supposed to take off this knob as well, I believe. Or maybe not, we'll find out soon. No, not really. Taking off this knob was not necessary. I'll put it back. So this is how the board looks. This, I believe, an Infineon CPU or something like that. Infineon is also a German company, exactly as Rohde und Schwarz. And here it looks pretty much clean, so there is no problem on this board. There's a small buzzer also, and this looks pretty nice. I don't see any. Maybe we see some soldering issue somewhere. I'll maybe take out my microscope and try to inspect every board. So again, this is how the board looks, and I think I see one issue. What could be the possibly causing the issue? I need better lighting there. So on this side, you see there is a pin. There's a pin on this side, and on this side there's a pad missing, and the pin is also gone. Okay, so this is what's causing the, I don't know, maybe it has a lot of pressure on it. The pins appear to be soldered. I do not see any pins to be broken. I don't know really. I'll find out now. So let's first inspect this thing under the microscope, and we will see how does it look. So now I'm at my soldering bench, and the instrument is sitting under my Mantis Elite, and it is not possible to just record a video into looking into this eyepiece. So I will switch to this the cam facility of this microscope, and we will try to record a video. This color balance is not very appropriate, but we'll still try to record a video. I think I have found something. I cannot show you right now, but there are a few pins which have been desoldered because of the force on this connector for some reason, and we're supposed to repair this connector, and we will try to find out first of all what is the part number of this guy, and once we find out the part number, then we will order this connector and try to repair the instrument. Maybe this is the primary issue which caused the fuses to blow. I do not know right now. So we have at least 2 issues. Fuses are blown and this connector is broken. Now we are looking at the output of my Mantis Elite cam, and you can see this image is not the best quality. This Mantis Elite has a somewhat low quality camera. It is not meant to be a USP microscope, and if you go and look into the settings, it's only like 12 fps, and we can change it, but then brightness and everything else get affected. But for now it should be okay. I just wanted to show you that I have found one more issue, that connector pins are getting damaged, and then we will go from there. Okay. So let me focus for you. That is also one challenge. Focus for microscope and focus for camera is different. Somewhat different, not very different, but I don't know if you can see or not. But I definitely see one pad damaged. This pad has been lifted off, like pad behind this. These front ones they are all okay. But the back one, this is lifted off. These two are lifted off, and at least few pads are lifted off. I believe this connector is Konski, and we will change this connector, and we will try to first of all try to find out which part it is, and then we'll try to look for a replacement, and then we will go from there. So let's move back to the bench, and maybe I'll show you how I'm going to look for the part number actually. So no, it's not 80 pins, it's like a 25 pin row, and it's a 50 pin connector. 50 pin connector, and I do not see any manufacturer marking there, because if you can see, the bottom side is completely covered off, and you do not see any manufacturer marking on this side, of course. But we have one more clue. The mating connector is pretty much exposed, and we can look there. So this is the connector which mates to the other connector, and I see some number, but I believe this is going to be date code or something like that. It is not going to be, this code is not going to be the manufacturer part number. And okay, I think I have found the clue. ERF? No, it is. If you look closely, I don't know if maybe I need to supply you a little bit light so that it's lit up from some other angle as well. So their markings ER and I. So this ER and I is a connector company, a known connector company, and you can see on the right side, it says A25. Says right here A25, so it's definitely a 50 pin connector, 2 rows, and it says A1. So this is the first row, and this is the 25th row, and 12 line ER and I. So we just need to look for the correct connector, and then we will be able to find a replacement part. Just for the sake of inspection, if there is any pins damage on this side, I do not see any damage of pins there. These pins they all look good. On the other side, yeah, they look somewhat dirty, but none of them seems to be lifted. If needed, we can reflow them as well. So what my theory is, most likely this front bezel got a lot more force, and that's how this connector got damaged. So let's move back to my computer, and we will try to find. So it was, I believe our connector something looked like this. Yeah, you can see Fumsik Polik means 50 pins, and lateral plate is stacked with a PCB connector. It's in German because I'm in Germany, and something like that. I do not know if our connector has notch like that. Maybe I'll get that thing. This is our connector, and you can see it also have a notch on the sides, and on the right side we have a male receptacle. On the connector goes in, but pins goes into this. So I do not really know which orientation this is, but it appears to be we need something where this connector can go in, and they are exposed pins. So the connector which is displayed on the screen, it's not the exact connector, but it can give us in the right direction. So we are looking for the correct part. We just haven't found any exact part number or something like that. And maybe we'll look for this particular guy and look its data sheet and something like that. Okay, I was more looking for catalog or something like that. So we will take this part number. So this guy, most likely this guy looks like our connector, because you look at it and yeah, this something like this, because it has exposed pin. I don't know if you can see or not, but on the front side it has exposed pins like that, and it's a right angle board to board, 50 pins, 1.27 millimeter pitch. You can get samples if you wish to, and I do not know, maybe we just need to order some parts. This appears to be the connector. Maybe we'll go back and look for this T. Maybe this, I think this NE is acquired by TE, and we need number of positions, maybe number of rows, and then we'll choose the number of positions. How many positions does this have? Because I'm confused if it has 25 position or 50 positions. 50 positions means 50 pins. Sometimes some vendors have it 25 position. So 50 pins, apply filter. Because these are definitely not our connector. And maybe we'll choose something as board to board. And we know the pitch as well, so we can choose the pitch as well, 1.27. And I do not know the stack height and stuff like that. Is this the same connector which we looked at? Yeah, this is the same connector, 1547 765. And this is, yeah, okay. It appears to be the connector which is mounted on the PCB, on the front PCB, because you can see it's vertical and has exact same number of pins. It may be they are very tiny and very minute amount of differences between these connectors, so you have to really watch out carefully, but we can never be certain. So most likely I'm going to just order some connectors and try to find out if they match. This also looks like something. So yeah, okay, look at this. Okay, I think we found the exact part. You see these notches, and I can see these notches are also available. Go back. So these notches are also available there, and I guess and I believe this is the part. There is no other similar part. There are only two similar parts. There are only two parts which are pretty similar. This 05459 6E and 154765. So you see this image is pretty low contrast for some reason. There are no notches here, and I see notches exactly there. So this is our connector. This is our exact connector. If you look at the side, this is what kind of peg it has, and this is our connector. I'm pretty sure on that. Let's open. So this is our connector. So I will order these parts, and then this sample is not available. Maybe I'll look for this part if anywhere it can be found. Yeah, so Mauser, it's on stock, €6 or something like that, and they are even, I think there's somewhere even better images available. Yeah, so look at this. This is our connector. I'm pretty sure on that, and I will order both of them because I'm not sure. I will order this 154765E. I don't know if it is available on Mauser. It is also available on Mauser. Okay, so we have two possible candidates. These both of the connectors will be ordered, and we will try to find out if they. So it's roughly 2 weeks after I first started repair of this HMC8042, and connector has arrived. And if you see, it fits pretty much very closely, and I have verified it offline, and they matches pretty much perfectly. And if you do not believe me, we'll take this guy and if you plug it other way around, it should fit perfectly. I will not completely seat it because these pins are currently not soldered, so they will not be able to come out if I seat the connector properly. So this is our connector. I will solder it offline because it's quite a hectic task, and then we will get back from there. So I have got the connector soldered, and there were few pads which were damaged. They were also repaired, and now we will try to connect the front panel and we will see how this instrument behaves. I hope it will turn on now, and as we see that both of the input fuses for both of the channels are damaged or blown, then it most likely will not have any output, but we will still see a boot up. And let's get started. So I will put it as upside down, and both of the flanges will go in. Okay, so this connector, if you look closely, and it should fit perfectly. As simple as that. So connector is in. I would install screws because I'm scared that it will get damaged one more time. So at least 2 of the screws I will put. I should have put the bottom one, but okay, we will put all 4 of them. So 3 screws are in. Let's put the 4th one as well. So we got the whole power supply set up. I have not put the power. So everything is in, and the whole thing is connected again. So let's see what does it do when I turn it on. Okay, fan is on, so it means at least the unit has power. Okay, unit has power. You can see this power on button, it's lit up. Let's press it. See if it turns on. It definitely tried to do something. Okay, so it does turn on. So this was the issue, I believe. I do not think I can turn on the output. Let's see if I can turn on the output. So I can turn on the output, but there is no output because I have told you these fuses are blown. I will try to replace those fuses, and we will see what effect do they have and how the repairs proceed further. So I will replace those fuses offline and we will see from there. It turned out the issue is quite severe, and it's not just the fuses that are blown. And this instrument has a little bit more problem than that. I will try to explain in a bit. You remember we removed this connector and tried to solder a new connector there, and it didn't fix the issue. I did not notice at the time, but you must understand this big fat microcontroller or this big fat processor in the front, it talks to these individual channels. For example, there are 2 PIC microcontrollers there, and I believe they are DS. They were PIC 33, EP 64 or something like that. So the big microcontroller or the big CPU talks to these microcontrollers for individual channels, and for some reason it cannot reach these guys. I do not know what's the reason. There must be a communication happening between these big microcontroller, the big processor, and these two microcontrollers, and this communications happen over this connector. I have checked again and again, all the connector pins are soldered and they all have a pretty good connection. Maybe there is something else wrong with the instrument, and as it turned out that the problem is still there. So how do I knew that there is a problem? I'll show you in the front, and for a comparison, I have a luck that I have one more same power supply. It's a 3-channel unit. It is my standard HMC8043. I even have one more, so I have total 3 HMC units, and they are all right now helping one another to get repaired. The good and nice thing about this HMC8042 or 43 is that it gets powered from a 48 volt supply, just a single 48 volt supply, this supply, and it gets powered from it, and there is only one 48 volt supply, there is nothing else. So same thing as in this case, you can power it with a benchtop supply. Right now I am using my another HMC8043 to power both of these units, and they both are connected. This is the benefit of having a stackable. I can use both of the power supply at the same time, but I'm powering both of these instruments by this power supply. So this power supply emulates SMPS, and there is no high voltage hanging in there, so I have both of these units powered by another power supply, and we will do comparative measurements. We will try to find out what is wrong with both of these instruments. I will compare we will compare their signals, and we should be able to get a decent result, because I believe they communicate exactly the same way. The same connector is used to communicate to this board, and the same connector is used, of course, to communicate to these microcontrollers. So currently the problem is that primary CPU cannot talk to both of the channels, and it cannot talk to other stuff as well. That is my presumption. LAN and everything works. LAN and USB I have tested. If you look in the corner, there is a differential channel going from this connector. Right next to the fan connector, there is a small inductive element. This is the filter element, and this is hooked up to the USB. It's a differential pair. I can see that. Maybe see it better here. Same stuff. You can see near to the connector there is a USB going. So USB and everything else works with this instrument. It's just that instrument cannot talk to both of the channels, and I'll show you how does it behave. I'll power both of the instrument, and I'll show you what is the difference between them. This is powered, this is powered. So both of them says HMC8043. That's not appropriate. It's supposed to say HMC8042. I have seen HMC4082 booting before this instrument. I got it as broken, so I don't know if this does it, but I'm 100% sure on that. I can go in the setup menu as well. It shows the model number and shows HMC8040, and there are some information which is supposed to get displayed here, which is also missing. So this instrument somehow cannot talk to the individual channels, and that is our problem right now. So this is what we are trying to do now. Both of the instruments are set up. I'll be probing with my RTP2004, and you will see a recording of that from the web view. If you look at my functioning HMC8043, there are a few chips. For example, this is one optical isolator, and this is one optical isolator. To be able to front board, to be able to set the voltages, this front board need to communicate with this microcontroller. I'm pretty sure the communication is going off over one of these microcontrollers, and we need to find out what kind of communication link it uses, what kind of signal it is, UART, maybe SPI, or maybe just one wire. I have right now no idea. And you can see there is a switching regulator somewhere down there. Maybe let me zoom in. So this little part, it's a switching regulator. This is what primary side regulation. Secondary side regulation is here. So when the 48 volts come from the primary power supply, this guy regulates it to maybe 1 or 2 volts above the output voltage, and rest of the regulation is done by the linear regulator. So this switching regulator, as the transformer suggests, it's an isolated switching regulator. So most likely the signal of controlling, I don't know, this switching MOSFET. It is going over through this optical isolator, because this guy sits on the secondary side, on the output side, and he needs to control the MOSFET on the input side, because that's where they will do switching. Otherwise transformer will not work on DC, of course. So this is a regulator section. This is the microcontroller which controls the output of the unit, or control the function of all these things. Primary regulator regulates somewhere 1 or 2 volts above the output voltage, and output of this regulator will definitely change when you change the output voltage. And the secondary side regulation is done by here. This is the linear regulation stage. I have mounted my camera on a tripod. Now you should be able to easily see what I am probing at, and I will do comparative measurements with my non-functional HMC8042, and we'll go from there which signal is what. So this is how we are going to debug, and you will see on your screen where I am probing, and also you will see this recording of the web view of my RTP2004, and I'll show you what are we going to probe first. So the optical isolators which are used in this part are this SI8431, and this appears to be quite high speed part for an optical isolator for 150 Mbps. And let's look at the footprint of our exact part. What we have 8431. We are interested primarily in the footprint itself. So 8431 has every part has a bidirectional channel, so 2 of the channels are going in, so pin number 1, 2 and 3, channel number 1, 2, 3, 2 of them are going in, 1 of them is coming back, and this is the primary side VDD where you send and receive the third channel, and this is the secondary side VDD where you receive and send the third channel. Okay, so this is what we are going to use. I'll show you what did I found. I think I'm onto something, and I'll show you. There are some activities going on both of the isolator which is sitting right next to the transformer, and isolator which is sitting between the channels. I'll point my camera to the PCB, and we will see where I probe and how does it look. So as I pointed out, this is my communication isolator. There is a communication line going from the primary board all the way to these isolators and every channel, and similar stuff. Communications lines are going between these isolators and the transformer and switching element and stuff like that. So we'll probe the pin number 3 first, and we'll see how does it look there. So we are probing pin number 3 of the optical isolator, and you can see there is some kind of digital signal probing there. We will try to zoom in and try to take a look at it, what exactly it is. Let me remove this counter a little bit far away so that you can see the signal better. Okay, and maybe I'll zoom in a bit. I'll zoom out. Yeah. So this is the kind of signal we have. It's a little bit flickering, so it's hard to see. Maybe I'll do a single capture. So this is how it looks. Most likely it is either a one wire custom protocol, or is some kind of UART, or maybe there is a SPI, and we will see a clock on the next line. So let it run and we will probe the next pin. This is the pin, or this is a signal which goes from the board and goes into these microcontrollers. It's driven by the CPU and is controlling these individual channels. Next channel is also in the same direction. I do not see any activity on this channel. Let me turn off the output. Maybe we will see something. So I am now changing the voltage, but it's not doing anything. Maybe it's some kind of OTP protection or some other thing. I cannot tell you what this signal do. This signal is coming from the, wait, let me probe. I cannot probe it. We'll leave it in the auto mode it is. So pin number 5. Pin number 5 is 0. This is coming from the CPU. Sorry, this is coming from these individual microcontrollers or these individual channels. There may be some status signal. It also, let me check if turning on the output and does something. It does not do anything at all. So these 3 pins which we probed, only one of them have signal activity. 2 of them are at this moment when we are probing, they are at least static. I do not know which signal they carry. So let's look at the other isolator, which is driven primarily by the individual channels. So this is pin number 3 of this channel, and I do not see, oh yeah, I see activity, but I am not on the same ground reference. So this activity is somewhere where I cannot trigger. Yeah. So now we are triggering. It looks a similar kind of signal. I believe it is a UART, because you must understand there are only 6 connections between these boards, and if one of them at least is used as a control pin for the MOSFET, for the switching element, and there is only 1 pin remaining, and you would need 2 clocks, I believe, maybe for both directions. Then maybe if you're using SPI, you can live with 1 clock as well. So if the next pin which I probe, or the up next, only 2 pins are left from probing, and if none of them is clock, then this is a 1 wire or some custom UART or stuff like that. So let me run the OSCE one more time, and it's running. So you see 1 more signal somewhere there, and next pin. This appears to be the switching frequency or the switching. Let me zoom in. So this is how it looks. It is, I don't know why it's triggering in such a bad way, because I'm set to trigger on both rising and falling edge. Okay, and now OSCE is better. So this PWM should change when I change the voltage. Right now it's at 7 volt, and you can see when I increase the voltage, this low time, maybe this is the on time for OSCE, maybe this is the on time for the MOSFET, it changes. Now at 32 volts and now at 1 volt. So this is definitely switching element, and you will see this is maybe going all the way there or there, I don't know, there it is there. Look at it. So we are probing the MOSFET itself, and let's run the oscilloscope. So we were probing the MOSFET. You can see there's a waveform visible there. I'll show you that's the same waveform which is getting over the opto-isolator. Okay, so maybe we'll zoom in a little bit more. That's too much. Okay, and right now we are set at 2 volts, and I'll change the voltage, which I showed you before. So depending on changing the voltage, this waveform changes the shape. And same thing happened here on pin number 4. We have exactly the same thing. So when I change the voltage level, the output voltage, the duty cycle of this PWM changes. So now it's thicker because it's 15 volts. Now it's thinner because it's 1 volt. Okay, control signal from this DC-DC converter is going there to do pre-regulation for the output linear regulator. Okay, and now what do we do? And now we're going to probe the 3rd number pin again, the communication line. This 3rd number is exactly same on the channel 2. And let's put the trigger point somewhere up, and we need to set the time base to higher. This is too much. Yeah. So you see the three distinct packets or digital activity on the bus, and I believe it is UART. And if you zoom in completely further in, and you will be able to see individual bits. We will measure 1 bit, We will try to determine its width, and you can see my cursor, they are magically aligned, not perfectly aligned but aligned with it. So 920.81 baud rate, that's the baud rate. When you measure a 1 bit timing for a UART signal, you can easily determine the baud rate. And let's zoom out a bit. I don't know why I set it to auto. Zoom out. I'm using my mouse. My oscilloscope supports a mouse, so I can look at the mouse. Okay, 50. And let me look at the acquisition menu, but I'm setting the memory depth to because the doesn't look very good automatic. Yeah, 6 kilo sample, a little bit less. Okay, so this is how your bus looks like. I will set up a decoder using a protocol decoder, and UART decoder I need, and I need what are the baud rate I need. If you remember correctly, we defined a predefined baud rate, user defined baud rate to around 920 kilobaud. Okay, it's set to 930. I don't know why does it do that. Let's change it one more time to 920,000. Enter. Okay, now it's set 91921 is close enough. I don't know why this oscilloscope does it. Maybe this has predefined stuff and it want to align to those predefined stuff. So you can see on your screen there is a big fat packet, and the packet says 152 AE and something like that, because we have multiple packets running, so they may not be having all the same data. So let's use a feature of this oscilloscope. It's called bus table, and all the 3 packets which are visible on the bus right now, I believe these packets are repetitive and they come so often that trigger is aligned to them. And you can see on your screen that this is definitely a UART bus, because it's quite obvious of a data 124 5050 AE AD AB. So if it would be some kind of one wire or something like that, then you would not make this much symmetrical sense or mathematical alignment or any this pattern, and you will not see it ever. And you see it, it means it is aligned, and we have a UART signal. Okay, so let's probe this other UART as well in the similar way. This is the output on the normal ground reference, and you see this also have a repetitive signal, and the signal says 01500A 5001 AD. Okay, so this is what microcontroller is sending back to the CPU, and this is what CPU sends to the individual channels and to be able to control them or set something. I don't know what does the AE AD AB means, but we will figure out later. And now we will change the output voltage of channel number 1, and we will see if this AD AB AB something changes. Okay, so you get a new type of packet. This value doesn't change, but you get a new type packet, and packet begins with 0101. Okay, and normal packet begins with 0150 or 0250, and this packet begins with 0101. So to be able to capture this packet, either we do single capture and try to get ourselves lucky, but I will not do that. I will do what? I will set up a trigger on my oscilloscope. My oscilloscope can set some advanced triggers, and then we will take a look how advanced trigger can help. Okay, so we remember set it to 1. Okay, and now it's in auto mode, normal mode. Now it will wait for the trigger, and yeah, look, we are capturing only the packet which we are interested in. So magical part is that the 0101 is repetitive and the rest of the 3 bytes are not repetitive, and I'm pretty sure the rest of the 3 bytes are some kind of value. And I'm right now at 3 volt. Right now I'm at 0 volt. Now you see that there is a hexadecimal FT. This is 1 volt, 2 volt, 3 volt, 4 volt. Let's go back to 0 volts, and I'll change only 1 millivolt, 2 millivolt, 3 millivolt, 4 millivolt, 5, 6, 7, 8, 9. So 9 millivolt appears to be quite aligned with the second last byte. This is 10 millivolt, A means 10, 20 millivolts, 12 millivolts now, 13 millivolts, 14, 15, 16 millivolts. Okay, so let's do 255 millivolts. I'll set the 2. Now 5. So at 255 millivolt you have value of FF as pretty much aligned. Okay, and let's do 1024, 1 volt and 0, 25 it is right now, and 24 is it. So I am outputting 1.024 volts, and the hexadecimal value is 400. I don't know what's the last byte, maybe it's a checksum, because they may need to verify the thing, and or maybe CRC, I do not know what is it, but first two values are definitely channel, or something like one of them 0101, the one of them is channel, first channel, and second value may be representing the value type or something like that. You can set OTP, electronic fuse, and everything else. There may be multiple parameters, so one of them is going to be parameter, one of them is going to be channel, and two values or two hexadecimal values are what do you call it, this 400 means 1.024 volts. It's very very basic protocol. One LSB means 1 millivolt, and F9 appears to be hexsum, checksum, or some kind of hexadecimal somewhere. Okay, now I'll probe the channel number 2, or maybe I'll just change the voltage on channel number 2, and we don't see any protocol or any bus, but we need to remove, what do you call it, we need to remove our advanced trigger to find out what kind of packet will be coming for channel number 2. Okay, so now I'm quickly changing the voltage of channel number 2, and you see the first digit has changed from 1 to 2. Okay, so this is channel number 2 definitely. So let's go back to the advanced trigger on the bus, and we will set the trigger to something else. Okay, so you remember 2 was channel 1, and 0 was channel, and 1 was channel 1. Value 2 was channel 2 and 1 was channel 1. So I have set the last two digits to hex, and we will see if we capture now both of the packets. Okay, now I'll first vary the channel number 2. You see there, maybe I'll set the same value. 3 volt it is right now, 4 volt it is. Okay, and now I'll do the channel number 1, same thing. So we capture both of the packets. This is channel number 1. Okay, and this is channel number 2. So first byte, which is displayed on this hexadecimal display, 20113, channel number, I believe this is the value type, the value itself, and the CRC or some kind of checksum. We can just do checksum on all the value, then we can figure out what's the algorithm it is using, but it doesn't take quite a bit of time to be able to control these signals. Let's try to vary the channel number 3 as well. I'm selected channel number 3. Let's see if it get capture. Okay, the channel number 3 doesn't get captured because the first byte is not matching. I'll set the trigger to be able to match, but it should match. If 1, 2, 3, then it should match with 3 bits. Maybe it has some other value. We'll do like X, 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 X. XX means doesn't care. Rest of the value should be 0, and last nibble should be some value. Okay, so now I'm varying channel number 3. Okay, now I understand. So value 01 means channel 1, value 01 means channel 1, value 2 means channel 2, value 4 means channel 3. They are setting individual bits. So first bit is set channel 1, second bit is set channel 2, third bit is set channel 3. Okay, and you see the same stuff is happening, value is changing. Now I'll change the current on channel number 1 and we will see how does it look. Right now it's 1 ampere. Okay, so as I told you, now packet is 01 and 02. It is representative of the fact that this represents channel, this represents current. When 1 is its voltage, when 2 is its current, and again this is these 3, what do you call them, 3 hexadecimal values. I believe they are current. Let me adjust the current to absolute 0 and we will see if it goes to exactly 0. So right now we are at 500 microampere. So last, this 05 means 500 microampere. So LSB in the case of voltage is 1 millivolt. In the case of current, it's 100 microvolt, 100 microamperes. So 10 means 1 milliampere. Okay, so I guess we have decoded the protocol, how, what do you call it, how does it controls the supply. And let's look at the outputs as well. How does the output looks, and if we can understand if we can make sense of the output as well. Okay, so trigger will not work that easily. I'll remove the bus table maybe. We need to go back to the normal trigger because we need to understand the packet format first and then we can set up a trigger. Okay, and maybe I need the bus. Yeah, it would not trigger because it's 015000 There may be, if this is the channel number and this is some kind of packet type, there may be more reports coming back. Is it triggering? Yes, definitely triggering. Let's go back to 500 micro. Okay, there are 2 packets coming. And there are more packets coming or not? 1 milli. No, that will be too much. I will not decode that long. Again, too much. This is the issue with the sample rate and acquisition memory and everything else. You need enough sample rate even for this UART signal. So we see report is coming for channel number 1, report number 50, report number 52 is coming, and sometimes we see other messages are also there. So I'll change the set voltage and we will see what changes. Right now set voltage is 1024 volts. I'll set it to 0. Okay, you see that value here, it changed from 400 to 018. Let's set it to 0. Right now it's 0, value is also 0, so report says 0. 1 millivolt, value is also 1 millivolt displayed. So this is the voltage reading. Okay, and how would I check for current reading? I need to short, or we need to put some load on the circuit. Okay, I have put, now I'll connect a load. Move this a bit because my tripod is in the way. So voltage and current, they are being reported in the same message. Right now voltage is 0 volt and current is flickering between 0.5 milliampere to 1 milliampere. I'll increase the current because I set it to very low of a value. Now current is a little bit more, 15-20 milliampere. So this is voltage and these 3 bytes are current, and last one is CRC or checksum. I do not know what is this. Maybe this is reporting channel is on, not underloaded, not overloaded, or maybe I'll look if this value changes. Right now I'm my instrument is current limited, and if this value 003 changes to some other value, maybe it's representing current limit or not. Yeah, okay. So right now my channel display is green, so value is 1, and now I will connect. My channel is red, means it's current limiting, so value is 3. So this is representative of the channel status, if it is overloaded or short circuit or current limited or voltage limited. One means at least voltage compliance, and second means that we have reached the current limit maximum. And this is current, channel state, voltage. So same thing will happen for other channels as well. One, instead of one, you will have 2 or 4, and you will see what is the value. So we have completely understood and decoded the protocol, how this UART HMC8043 works, what are the signals going over these individual octo isolators. We did not understand 2 of the signals here and 1 of the signal there, but it may not matter, because maybe this is what we are going to probe now, and we will probe on the dead instrument and we will see if we get similar results. Let's move to a dead instrument, and we will try to probe that. By the way, there is one more thing I discovered, that on this pin near to the microcontroller there is a continuous running clock available for some reason. Let's remove the UART and set it to auto. Maybe I'll zoom in. So this is some kind of clock. I have checked it. It's not aligned with the UART signal. So it's some kind of signal is being outputted from the microcontroller. Every section has it. I don't know why they have it, but they all have it. Okay, so this is a representative of the CPU is working or not, or maybe the microcontroller faulty or something like that. Let's move to my faulty unit, and we will check that. So first thing we will check is for these control signals, if they are coming. And check on the number 3, and you can see on the scope number 3 pin number is constant high, and there is no activity happening on this. I'll set it to normal mode so that we can see if the trigger is there. No activity whatsoever, trigger is not there. Okay, so there is a possibility that microcontroller is faulty, or the connector is faulty. It's not sending anything at all. So I'll turn off the instrument and turn it on again, and if we see if in the boot up there is something coming up. Yeah, okay, so microcontroller is definitely not faulty. It sends some boot messages. We will set a single trigger, or maybe set a normal trigger, so that we can see the message. Turn it off again, and it says 004D1B. Turn it on again. It's booting. It sends 15C82. I do not know what 5C82 or 0300FC means. Okay, so there is some activity happening there. Okay, so let's look at the output of this guy on the same, reflectively same pin number. Okay, on the other side, let's turn it on. It will not be capturing so easily because we are not the same reference, if I remember. Let's set the auto mode. Okay, so I turn it on. I don't know, there is no activity. I turn it off again. Maybe I'll set both of the channels need to be, I need now 4 hands, but I have fingers, I can hold it. Never do this because it's very risky. And these probes, they are not spring loaded. Generally, if you have a better quality oscilloscope or expensive oscilloscope, you will have a probe with a spring contact. And this RTB2004, even though nice oscilloscope, it's not that expensive, so it doesn't come with the probe. I'll set up the probe trigger on channel number 2. Trigger level is going to be same around this volt, and we'll set to normal mode. And now we will see if there is activity happening on the same time when I send something. Okay, so you see on first channel there is no activity at all, and the second channel, which is the input, there is activity. So for most likely this chip is either faulty or it's not getting what it's supposed to do, not getting the signal in appropriate condition. We'll check for the voltages first. Okay, I'll set the scope again into auto mode, and trigger need to be at channel 1. 3.26 volts. Okay, this is the primary side, and it's coming from here 3.3 volt, and this is the secondary side. And if you look at it, it's 0 because we are not on the same ground reference. We need ground reference from somewhere. Okay, it is still 0. So this guy is always 0, and this is not right. This supply, as I pointed out before, coming from this area, and there are multiple regulators. There is a fuse for this section of regulators. There is a fuse for whole device. There are fuse for individual channels. There is a fuse for this regulator as well. So we will measure. We will flip the instrument. We will measure on the fuse itself if it is getting power. If it is not getting power, these things, they need a dedicated 3.3 volt supply, isolated from one another, from the whole instrument, to be able to function. And this 3.3 is not coming, you will not see any activity. If you want, I can measure this UART here, and you see there is no activity at all. This is a clock signal. It will be visible even without the ground reference. So there is no activity whatsoever. This section is whole dead. It's because it's not getting its 3.3 working power supply. Okay, and let's see if, let's flip the instrument. I'll show you where the fuse located, and I believe I missed to measure that fuse, otherwise I would have saved this hassle of debugging in every single section, decoding a digital protocol and everything else. Let's flip the instrument, minding that we do not short anything. If you see, this is the fuse, and we'll measure with the multimeter if it is shorted or not. It still has continuity. Right now it's turned off, instrument is off. So we'll use my multimeter and check the continuity on this. You will be fooled to believe that it has continuity because it beeped for a second, and if I check other way around, it will beep even longer. Because there are capacitors everywhere, and when you initially connect them, they do get small continuity or current flow, and which makes the multimeter believe that there is a continuity, but there is no continuity there. So you probe and it's blown. This fuse is blown. I'll repair this and we'll get back and try to repair the instrument. If you want to measure the voltage, I'll turn on the instrument and I'll show you with my multimeter. I'll show you with the oscilloscope itself. It's unisolated side, so it says greater than 10 volt because the time base is quite big. It says 42 volts, which is I'm feeding in, and here it says, of course, 0 volt because the fuse is blown. So that's it. We'll repair this fuse. Most likely we will get the instrument up and running once the power is established. This thing will start to work. So I have repaired the fuse. There's a new fuse installed there, and we will see how our instrument behaves differently. We'll probe the same thing. Probe pin number 3. If there is activity there. I don't see any activity. Yeah, because the time base is wrong. Sorry, the voltage base is wrong. It's supposed to be 2 millivolt, 2 volts per division. Now I need the appropriate trigger. You see, there is activity going on, and because it's continuous, I believe the both channels are working and the instrument is communicating. I'll show you the display front. I can already see it's working. Just for the sake of verification that it really works, let's measure the output of this signal, and you see this is settling down. Let's go down. Yeah, so both sides are working, communication is on. Let's measure the clock. Clock is also available. Measure the output. Third number. Output is also available. And let's look at the instrument front. Okay, so on the instrument front, you can see there's a little bit more display available, some statistics or something like that. Let's turn on the channel 1, and you have 1 volt. If you want to see, I'll turn it off now and I'll show you how it's differ when turning it on. It's different. You remember? Initially it was showing HMC8043, now it shows HMC8042 at the boot up. I believe this unit is completely fixed now. If you want, we can test the current as well. Maybe plug it to channel 2. Shit. Okay, channel 2. Exactly 500 milliampere. So it's regulating the current as well perfectly. Both of the channels are absolutely wonderfully full functional. I'll do further tests, make sure that the instrument works, and we will close the instrument and put everything back together and make sure that they still work even after putting it back together. So that's it for this video. You can visit my website www.circuitvalue.com. Bye for now.